know that, don't we? What were those three numbers when we plugged them in? We had -2, and it spit out what? -44. And at 3, what did we get? 81. And what about it at half? 37 halves, right? Which was about 18.5? Yes? So I look at that now and I say, look, when I draw this, what's the biggest y value that I'm going to need? The biggest y value? 81. What's the smallest y value? -44. So I need to make sure I draw this, scale the y-axis so I can fit it all on here. You know what I'm saying? Like I'm not going to say 1, 2, right? Because I'm going to be off the thing. So instead of doing that, let's do something like 20. Okay, so I'll do like 20, 40, 60, 80. And then down here, same thing, -20, -40, -60. You get the idea, right? And then plot these points. At -2, I'm at -44. So we're just going to eyeball this somewhere around here. All right? Y'all see my point? -2, -44. And I would actually go one additional step. I'd probably label that point. -2, -44, like that, so people know what it is. And then I can go ahead and take care of the half because it's right here. That was about 18.5 or 18.5, so that's about right here, roughly speaking. 1/2, 37/2. Wait a minute, was it 37/2?
Yeah, it
Was, okay. And then at 3, we're way up at 81. We're almost done. All right, now what we'll do is we'll start with this left piece. My graph to the left of -2 must look like that. And it needs to connect to this point. So you see that point right there? To the left of it, I'm going to draw that picture. So I just need to draw the left side of a smile. And I'm going to just draw it with an arrow like that. Then between this point and this point, right? Between these two, it must look like the right side of the smile. Okay. Okay. I think that's okay. And then from 1/2 to 3, it's got to look like the left side of the frown. And so it looks like that. And then from this point on, it looks like this. Voila.
Mine does not look near that pretty, but okay.
So the method that the book teaches is nowhere near as efficient.
Well, they just use a sign chart, and I mean like a plus minus thing.
Okay.
It's just, I don't know. I invite you to go look at it. It's a mess. I mean, to me, it's messy.
Yeah. No, that's pretty convenient.
Pretty straightforward. Okay. Now look, there are some things that you might look at this and you might say, hey, couldn't we add additional detail to this? Like perhaps you could find the x-intercept, right? Like there looks like there's an x-intercept here. How do we find x-intercepts of functions? We set the original function equal to 0. Oh yeah, we could do that. We could do that for that one because we have a GCF. We could factor an x out. And okay. How about a y-intercept? It hits the y-axis somewhere, right?
That'd be 0.
So you could plug in 0. Okay. So you can tell right now that we're off a little bit on our graph. We're definitely off. Our y-intercept isn't in the right place. So guess what the next section is about? The title of it is curve sketching. And what it does is it brings in everything. So you look at x-intercepts, you look at y-intercepts, you look at symmetry, you look at all these things that you looked at in algebra, and now you tie it into the calculus and you get a perfect picture, almost perfect picture of what it actually is. Now, it is 2016, about to be 2017. We could type this into a calculator or computer, Wolfram Alpha, we could have the graph like that, right? So I understand you sitting there going, why spend 30, 45 minutes on a problem that the computer can do for me in a few seconds? I get that. I understand that. This is about a process. This is about you understanding the relationship between a function and its first two derivatives. That those first two derivatives tell you a lot about what the thing looks like. And this is the way it used to be done before calculators and computers. When you had to graph a function back in the 1940s without anything but your hands, this is what you did. This is the way they got good representations of what these functions look like. Yes, you could, but if you sat here and let's say you knew nothing about calculus, you would not be able to tell me what the local maxes and mins are of this function with any certainty. Well, they were what, at -2 and 3, those might be easy to get. But when these critical numbers become more complicated, like there's one in the homework I did right before this, I did the video on it before class, and one of the critical numbers was -1/√3. You're never going to find that by plug and chug, by just testing. You're never going to find an irrational number as an answer. It's not going to happen. So we can only get exact answers this way. All right, well that only took what, like 20, 30 minutes? So I might have time here for one more?
Yeah, let's do it.
All right, let's do one more. Let's do a harder one. You have for homework 1, 2, 3, 4, 5, 6 of these graphing problems. And before that, you have 4 problems where you have to do everything except graph.
So we have 10 of these.
So you basically have 10, but 4 of them you don't have to graph. It's good.
Saves us 3 minutes.
All right, I'm gonna do one straight off the homework that I did not do on the homework video. I'm gonna do number 33. And then next class, my class tomorrow, my Thursday class, I'm gonna do number 35. So if you're gonna go home and do the homework, I will have the videos online for the answers for all the homework problems except for 33 and 35. 33 I'm gonna do here today, 35 in my class tomorrow. So if you wanna know the answer to 35, you have to watch my lecture tomorrow from my Tuesday, Thursday class. So 33. And it's a trig function. The one from that I'll do next class on Thursday is a trig one, which you need to see. But this one is actually pretty cool too. All right, they use C of x. Yeah, let's use C of x. C of x equals x to the 1/3 times x plus 4. Yeah, let's talk domain first. Can we talk domain first? Because this is not a polynomial function. So we do have to at least address that possibly we could have a domain issue. The things when we think about domain are like, you don't want fractions where you might get division by 0, and you don't want like even roots, square root, 4th root, 5th root, because then you can't plug negatives in. So this x to the 1/3 really means what? What root is that? Cube root. And can you put a negative in here? Yes, you can take the cube root of a negative number. You can't take the square root of a negative number though. Yeah, like cube root of -8 is -2. Negative times negative times negative would give you back a negative. So the cube roots of negatives are fine. We don't have any division by 0. Our domain is all real numbers.
That's the first thing.
First thing, yep, always look at that. Because remember, your critical numbers are only going to be really, truly critical numbers if they're in this domain. So I'll put here real quick, domain of C is all real numbers, -infinity to infinity. This is problem number 33. Problem number 32, which I did on video, there is a domain restriction because it involves a square root function. So watch the video. All right, now derivatives. Let's go ahead. How would you like to do this derivative? You have options. You could do product rule. That's one option. Does anyone else see another option?
That's a quotient.
You could drop it. I wouldn't drop it though, because it's already just x to the 1/3.
Logarithmic?
No. You could distribute the x to the 1/3 through the parentheses.
But that seems like too much work.
That seems like too much work?
Would that just be x 4/3?
What would this be if I distributed that through? X to the 4/3 plus 4x to the 1/3. That's very clean, isn't it?
Yeah.
And that derivative is very clean too, because you can do them individually with no product rule. I like that. Can we do that? Yes.
How do you do the first one?
This is x to the first power. Same base. You multiply these two together. You add the exponents. 1/3 plus 1 is 4/3. X to the 1/3 times x to the first power. You add 1 plus 1/3. Get a common denominator. Yeah, add. You multiply if it's like x to the 1/3 and then raise that to something. All right, so derivative is 4/3 x to the 1/3 plus 4/3 again, because that's coming out, x to the negative 2/3. All right, while we've got it here, can we do second derivative? While we've got it there, just like that? Because we can do power rule again. C double prime. C double prime is 4/9 x to the minus 2/3 minus 8/9 x to the negative 5/3. All right. Yikes. All right, well, fine. That's what it is. Let's keep going. What am I supposed to do? Critical points. So I need to set the first derivative equal to 0. Let me start with that. Notice I'm using C prime instead of F prime. All right, so, oh man, I've got to set that equal to 0. I've got to set 4/3 x to the 1/3 plus 4/3 x to the negative 2/3 equal to 0. Does anyone see something I can do just right off the bat that'll make this a little bit nicer? Take out a 4/3, factor it out, and then how about just divide it out? Like divide the 4/3 through. Like divide this by 4/3, divide this by 4/3, divide that by 4/3, and it's gone, isn't it? You could equally say multiply both sides by 3/4, and that would cancel it out. So whatever, it's just the algebra. So x to the 1/3 plus, or what did I say that y'all like that I said that one time? Like it's trivial, it's, what did I say?
Common sense.
It's common sense, right? That's common sense right there. All right, so we good with that? This is a dangerous place right now, okay? Because the algebra I've seen students do at this point is like voodoo algebra that I've never seen before. You have to be very careful right here. It's usually not correct.
Is it x to the 1/3?
X to the 1/3 what? I don't know. I want you to, obviously I can do this, but I want to see if anyone has any ideas of what they would do here.
I have an idea. Ask you.
Okay?
You can divide out the x to the 1/3, right? And then
How do you mean divide it out? Like factor it out?
yeah, factor it out.
I don't mind factoring it out. That's okay with me. All right, so if I factored x to the 1/3 out, I think this is what you mean. Is this what you mean?
Yeah.
Okay. Then I pulled it out of here, I would get a 1 plus what would go here?
Is that just
x to the negative what? Negative.
I feel like it's gonna be.
They need to, what do they, whatever this power is, needs to add together to this, right? To get that? Negative 3/3. But what's 3/3? Negative 1. Look, I'm going with what you said. I agree, you can do that. It's not what I would have done, but it's okay. Look, this will work.
Well, you can set the alpha on to 0.
Yes, now it's factored, so you can set this one equal to 0. Now, initially you said divide out x to the 1/3. One thing you would not want to do here is divide this on both sides. You want to set that equal to 0. You have to include that solution. So this is working. Look, I've got two things so far. I've got x to the 1/3. I need to know when that's 0, right? And then the other thing I need to look at is when is x plus x to the negative 1 equal to 0? Right? That's what this is. This is just 0. Yay, we have one critical number so far. All right, and then, what the hell? Okay, how about this? How about 1 plus 1 over x? That's what it is, right? You don't like fractions? Let's clear it. Let's clear the fractions. Can we multiply both sides of this equation by x? Could we? Yeah? Multiply that by x, what do we get? Multiply that by x, what do we get? 1. Multiply that by x? 0. X is negative 1. All right. Two critical numbers. Are these critical numbers in the domain of the original function? Okay, but we're missing, there's something missing here. There's something wrong. Something was lost, and I'll give you a hint. It was on this step from here to here. What did we do? Multiplied by x, which you're allowed to do, so long as you promise me that x is not what? 0, right? Now, look, there is a problem. What if x is 0? Then it's undefined, isn't it? Okay. So what we're saying right now is that x is 0 and x is negative 1 are critical numbers. But truly, if x is 0, you're going to have a major problem, right? Look at this derivative. This right here, that's really 1 over that, isn't it? 1 over x to the 2/3. If I plug in 0 for x, what am I going to get? Division by 0.
But that's for the derivative.
That's right, which is what I'm working with here.
But the domain is of the original function.
But you can, okay, let's back up. What we said is when is the derivative 0, right? And we did some suggested algebra and we got these two answers. Said, look, if I plug in 0, I'm going to get 0 for the derivative. If I plug 0 in for x, I'm going to get 0. That's what we got, right? But that's not what happens. If we plug in 0, what do we get? Undefined. Something is wrong in the algebra. Now, I want to take you back to this step. I don't want you to forget what we just did, because that was all worth doing. But I want to go back to this. No, there was something in there that we missed, right? Like that 0, we got it, but that's not what we plug in to get 0. Something is off. So what have we been doing with the other derivatives that we've had? Anytime we had a derivative and we set it equal to 0, weren't some of them turning into fractions? And then we were getting if a fraction can only be 0 if the top is 0 type thing? Okay, I want us to look at this and I want us to write it this way. All right, that's the same problem, right? Okay, get a common denominator right now. Put these two together, so that's over 1. What would I need as a common denominator? X to the 2/3. X to the 2/3. So I introduce on the bottom here x to the 2/3 on the top x to the 2/3. Yeah? All right, what do we get on the top left there? X to the 2/3 times x to the 1/3. You add the exponents, you get x to the 1. So I get x and then plus 1 over x to the 2/3 equals 0. Now, when can a fraction be 0? Only when the numerator is 0. And that means x is -1. Isn't that the answer we had a second ago? But we're missing the 0, aren't we? We're about to get it, though. How are we going to get that 0 as an answer? By the does not exist. So look, this is the only number we can plug in to make the derivative 0. So with the algebra that we did, there was some danger in that because of the fact that we multiplied through by that x. You have to promise me x can't be 0, which means you have to throw out 0 as an answer. Okay, that's this. Now let's look at when is the second derivative not exist. I guess I can erase this. Go ahead. Did I say second derivative? I meant to say when does the derivative not exist? So, well, here's the derivative, right? When does that not exist? If I just rewrote it like this, right? Right there, where I drop that down, you can just look at it and tell me x can't be 0, right? So x equals 0 is a critical number. You could also have turned the derivative into that, right? You could have turned the derivative into this, and then looked at that and told me when that's undefined, when x is 0. Either way. So how many critical numbers do we have? 2. And so what am I going to do with them?
You're not going to make a number line.
Make a number line. And they were what? -1 and 0? That splits it up. Box these up. And test.
And this one we're plugging into the first derivative.
Plugging into the first derivative. So I'm going to go with, let's say, -2. Actually, you know what? I'm going to be a little clever. I think I'm going to be a little more clever. I'm going to think about what I need to plug in here. This is where I've got to plug it in, right? Into this. So because I'm thinking ahead a little bit and not just being a robot, I'm realizing that I need to plug it into this. That's another way. Oh, wait, this was negative. Shoot. That was a negative root right there. So I'll just put it on the bottom. That's the first derivative written a different way, isn't it? That's our first derivative written a different way. I don't like that 4. Okay? Guess what I'm going to choose for this number? For this one over here, something over here.
Like a -8.
Like -8. Because I want to be able to take the cube root of it easily. I can take the cube root of -8. How about in here?
Like 1/8.
I could do -1/8. I could do -1/8. Because I can take the, see, what I'm thinking is, what can I take the cube root of? And -1/8 is in here, isn't it? Yes, when you take the cube root of -1/8, you'll get -1/2. And then what about over here? 8. Actually, I'm going to go with 1. Because the cube root of 1 is 1. The reason I couldn't do that over here is because -1 was a critical number. Do y'all see that? Now, feel free to pick -2 and -1/2 and whatever else you want to pick, but just understand you're going to have to figure out what that is, so you can work hard or smart on that. All right, you ready? Let's plug in. What is f prime of -8? So we have 4/3 times the cube root of -8, -2, plus 4/3 times, what is the cube root of -8? -2 squared, 4. I believe we're getting exhausted. What is this? -8/3 and then plus what? 1/3, which is -7/3? Negative. It's a negative number. What does that tell me? Original function going down. I don't know if I'm able to finish this problem. We haven't even started the second derivative work on this one yet. All right, let's try and plug in -1/8. What happens if we plug in -1/8?
4/3 times 1/2.
So it'll be 4/3 times -1/2, right? Because you're doing the cube root of a negative number is negative, so -1/2 plus 4/3 times, now be careful here, cube root of -1/8 is -1/2, but then you're squaring it so it becomes 1/4 here. -4/6, which is the same as -2/3. This is just arithmetic, right? And then this one would become plus, I would flip the 1/4 up as a 4 on top and make that 16/3. But at the end of the day, it's positive, right? So we get plus. Function's going up. And then 1. I think 1 we can do pretty easy. 4/3 plus 4/3.
8/3.
Up again. Right? That went up again. Did not switch. Do I have to plug in 1 or can y'all can get 1, right? 1? Okay. All right. So let's just talk through it. I'm not going to write the answers up. Where is this function going up? From -1 to positive infinity. The fact that at 0 it flattens out, that's okay, because as you move through, it's just continuing to go up. So f is increasing on -1 to infinity. F is decreasing on -infinity to -1. Do we have a local max? No local max. Do we have a local min? Yes. I'll put that here. Local minimum, where does it occur? At -1. And what would happen if we plug -1 into the original function? -1 plus 4? 3. What's -1 cube root? Cube root of -1? -1. So what is it? So -1 times 3? -3? This should feel like all of your college algebra class, and then after you do a trig problem, you'll see it's like all your classes are actually coming together into one problem. There's arithmetic, there's algebra, there's calculus, there's a bunch of stuff in this. All right, I've got 10 minutes. Let's see if we can't get that second derivative. All right, let's see if we can't get it. All right, before I start setting the second derivative equal to 0, I think I'm going to spend some time cleaning it up first. Because I think we need to look at it in a different form than that one right there. So let me rewrite it. The second derivative, if I rewrite it, is as a fraction 4 over 9 x to the 2/3, and then minus 8 over 9 x to the 5/3. Can we get a common denominator here? This one right here, they both have 9. Can I turn that into an x to the 5/3?
Yes,
By multiplying it times x to the 3/3, right? So by x, really, right? If I multiply that times x to the 3/3, I get x to the 5/3 because I add them up. So x to the 3/3 is really 1, x to the 1. So I'm just multiplying top and bottom by x. Get it? That turns this into what? 4x over 9x to the 5/3, but it's really, when I put them together, it's 4x minus 8. And why do I like that version of the derivative? Isn't it easy to set that equal to 0? I can just say top equal to 0. Is it easy to look at that and see when it's undefined?
Yeah.
Yes, at 0. So I have two critical numbers right off the bat. Y'all got it? See how me cleaning it up makes it so much better? Okay. Second derivative equal to 0. Turns out to be 4x minus 8 equals 0, which means x is 2. Second derivative doesn't exist at x is 0. Just by inspection, just by looking. Now what? Number line? We might finish this one. Yeah. Here's my number line. I'm putting on here 0 and 2. Boxing them up because they're critical numbers. Partition my number line and pick some numbers and try and be clever. I still need to do a cube root, don't I? Isn't that a cube root right there? That's a cube root. I can do 1, yeah. How about we do 1 here? How about we do -1 will work, right? And then over there, what do you want? Let's do 8. All right, we're plugging these into the second derivative. What's f double prime of -1? C, thank you, thank you, thank you. Just checking, just testing you. C double prime of -1. So it goes in right, I'm gonna plug it into this one. Isn't that my nice clean version? Yeah. So what's the top? -12. I'm plugging in -1 for x. -12 over. So this right here means cube root and then to the 5th power. -1 goes in. -4 times -1.
So is that positive 1?
This means cube root. What's the cube root of -1? -1. To the 5th power, what's -1 times -1 5 times? -1. Still -1 times 9. -9. So you get positive, which means my original function is doing what? Smiling. It's so happy. All right, second derivative at 1. Now there's your -4 on top. And then on the bottom, hey, 1 to any number is 1 times 9. So we get negative number. So frowning. And finally, if we plug in 8, C double prime of 8 is positive on top. Do you agree? And on the bottom, let's just think about this. The cube root of 8 is 2, right? 2 to the 5th power is positive. Times 9 is still positive. So without actually getting the number, I know it's a positive divided by a positive is positive. And so I am smiling.
So just a quick question. So if we're just looking for positive negatives, is it bad to type it in the calculator?
Just type it in right. Type it in right. Yep. You need to be sure about it. Okay, 4 minutes. Number line's done. So now we go to that method that I said is a little different than the book. And I think we can knock it out pretty quick. I just need your help. Oh, we never found the inflection points. What are my inflection points? I am going to need this. We know where it's going up and down. Just, we're not going to write the intervals down. Where are my inflection points? 0, right? 0. And I plug 0 into the original function. 0. And then the other one is at 2. Ah, crap. Okay, so 2 in here is what? 6? 6 times the cube root of 2, which is 6 cube roots of 2. That's what it is. We can figure that out on our calculator in a little while. It's going to be bigger than 6, though. With me? All right, here we go. I'm going to run out of time, but I'm going to go fast. What were the critical numbers from the first derivative? 0, negative 1. What were the critical numbers from the second derivative? 0 and 2. I draw it from here vertical lines. I give myself enough room for 3 rows. The first row is going to be C prime, second row C double prime, last row or top row is C itself. Tell me about C prime. Down until I get to where? So down until I get to negative 1? And then what? Up. And it continues up. You sure? That's what it was? Okay, I'm trusting you. C double prime? It's right there. Look at this. To the left of 0, smiling. Here's 0. Smile, smile. And then between 0 and 2, frown. And then past 2, smile. Left side, right side, left side, right side, like that. The only way to go down a smile is come down the left side. Only way to go up a smile is up the right side. Only way to go up a frown is up the left side. To go up a smile, up the left side, up the right side. 2 minutes. Okay. Here's my x and y axes. Here's 2. Here's negative 1. And here's 0. Where are these points? I'll do them in red. So at 0, I'm at 0. At, where was I at negative 1? It was at negative 3? I'm going to say that's negative 3. And then at 2, I was at 6 cube root of 2, which is something like 6 point something or 7 point something. It's up here. That's whatever 6 cube root of 2 is. Is that all right with you if I just put that there? All right, let's connect it. To the left of this point, it's got to look like that. Between here and here, it's got to look like this, and you got to connect the two. Local min, right? Ooh, what's happening here? Here to here. It went from a smile, and it switches over to a frown, right? And then it goes back to happy, like that. Yeah? Did anybody graph it on their calculator? Is that it for the week for us? Yeah, I had a feeling that would happen. This calculator has some issues with it. It's having trouble. This computer's having some trouble with it. Yours looks good. That's perfect. Yep, that's good. But what you can't tell from your picture is, it's hard to tell from your graphing calculator where this is happening. But can you tell that that's happening at 2? I don't know. Probably not. Okay. Good luck. 4.3. 4.3 is your homework. We will come back. We're going to do a little more of 4.3 next time. But we're going to start adding in those other elements, which is, okay, let's look for the x-intercepts now. Things like that. Have a great weekend. If anyone needs their quiz from last time, there's quizzes up here. Edgar and Helika and Harrison.